When you look up at the night sky, it feels quiet. But that's just your eyes playing tricks on you, because if you do the arithmetic, and nature always respects arithmetic, the universe shouldn't be quiet at all. It should be roaring. Start simple. Our galaxy alone has something like 100 billion stars. Not 10, not 1,000, 100 billion. And we now know planets aren't rare decorations. They're common. Most stars have them. Many have Earth-sized worlds sitting in that delicate region where liquid water can exist. Now multiply that by the hundreds of billions of galaxies scattered across the observable universe. The numbers become absurd. It's like walking onto a beach and finding not one grain of sand, but more grains than you could count in a lifetime, and then being told only one grain might have life. That's not impossible, but it's suspicious. Now here's the funny part. Physics doesn't object to life. Chemistry seems almost eager to produce complexity. Carbon bonds in versatile ways. Water dissolves things beautifully. Energy flows from stars in steady streams. On Earth, life appeared relatively quickly once conditions stabilized. Not after 10 billion years. Not after endless hesitation. It popped up early, almost as if the universe had been waiting for an opportunity. So if the recipe works here, why not elsewhere? If the laws of physics are universal, and as far as we can tell they are, then hydrogen behaves the same way in Andromeda as it does here. Gravity pulls the same way. Light travels at the same speed. The same ingredients should produce similar outcomes. That's the quiet assumption. Behind modern astrophysics, the universe is consistent. And yet, when we listen, we hear nothing. No signals, no engineered radio patterns sweeping across the stars, no megastructures blotting out starlight, no unmistakable signatures of advanced civilizations rearranging their cosmic neighborhoods, just background radiation and natural noise. It's like expecting to find a bustling city and instead walking into an empty desert. This contradiction has a name, the Fermi paradox, but calling it a paradox makes it sound philosophical, like a riddle for late-night conversation. It isn't. It's a tension between numbers and observation. The numbers say there should be many. Observation says there are none. And physics doesn't like unresolved tensions. When theory and experiment disagree, something is wrong. Either our assumptions are incomplete, or our understanding of the process is flawed. Maybe life isn't as inevitable as we think. Maybe intelligence is a cosmic accident of staggering improbability. Or maybe civilizations don't last long enough to overlap. That's where the discomfort creeps in. Because the silence isn't just about them, it's about us. If the universe should be loud but isn't, then something is suppressing the noise. Something in the chain from star formation to intelligent beings breaks down. The sky isn't just empty. It's telling us something. And whenever nature whispers instead of shouts, it's usually because we're missing a piece of the mechanism. The terrifying part isn't that we're alone. It's that the equations suggest we shouldn't be. Let's suppose for a moment that life isn't the problem. Suppose microbes pop up all over the universe whenever conditions are halfway decent. Chemistry seems perfectly capable of that trick. Give it water, carbon, energy, and enough time, and it starts building little self-replicating machines. Fine. So maybe the universe is crawling with bacteria. But bacteria don't build radio telescopes. Somewhere between a single cell and a civilization capable of rearranging planets, something extraordinary has to happen. Not once, but many times in sequence. Cells must cooperate. They must become multicellular. They must develop nervous systems. Intelligence must evolve. Tool use must appear. Language, culture, science, technology. And then, and this is the delicate part, the civilization must survive its own discoveries. That long chain is what people call the Great Filter. It's not a mystical force. It's just a step, or several steps in that chain that are so improbable or so destructive that almost nobody makes it past them. Now here's where physics creeps in like an uninvited guest. The same laws that allow a species to unlock enormous power also make that power dangerous. Nuclear physics, for instance, is wonderfully elegant. Split the atom, and you release binding energy that was sitting quietly in the nucleus for billions of years. It's a triumph of human understanding. But the equations don't care whether you use that energy to power a city or flatten it. The same Maxwell's equations that give you global communication also give you automated weapons. The same computational principles that allow artificial intelligence to assist humanity might allow it to outpace or outmaneuver it. Physics is neutral. It hands you tools. It does not give you instructions. Imagine a young civilization discovering how to manipulate its environment on planetary scales. It learns to tap fossil fuels, stored sunlight from ancient life, and in doing so alters its atmosphere. It learns to engineer pathogens. It learns to automate warfare. Each breakthrough is a celebration of intelligence. Each one also increases the probability of self-inflicted catastrophe. There's no villain required, just statistical inevitability. If enough civilizations reach this stage, and if even a modest fraction of them miscalculate once, the silence begins to make sense. You don't need a cosmic executioner. You just need beings clever enough to access enormous energy and imperfect enough to misuse it. And here's the uncomfortable twist. We are at precisely that stage. For billions of years, Earth had life, but no existential risk created by that life. Dinosaurs couldn't split atoms. Trilobites didn't alter the climate intentionally. But within a few centuries, a blink in geological time, we have acquired the capacity to transform or terminate our own civilization. If the great filter lies ahead of us, it would mean most civilizations don't navigate this transition successfully. They discover the deep laws of physics, and those laws amplify their reach faster than their wisdom evolves. The silence then is no peaceful. It's statistical. It may be the quiet after countless experiments failed. And if that's true, the most important scientific question isn't where is everybody? It's, are we about to find out why? People often imagine the universe as a grand open arena. If someone out there builds a powerful transmitter and beams a signal into space, surely, eventually, someone else will hear it. After all, space is empty. There's nothing in the way. But that picture misses the most important detail. Space is not just empty, it is enormous, and physics places a strict speed limit on everything that moves through it. Nothing travels faster than light. That's not a suggestion. It's built into the structure of space-time itself. You can't cheat it. You can't engineer around it. The equations of relativity don't bend for ambition. Light moves at about 300,000 kilometers per second, which sounds fantastically fast, and it is, on human scales. Light can circle the Earth 7 times in a single second. Impressive, but now stretch your imagination. The nearest star system to us, Alpha Centauri, is more than 4 light-years away. That means if you send a message today, traveling at the fastest speed allowed by the universe, it arrives 4 years from now. If they respond instantly, you wait another 4 years for the reply. One simple hello takes 8 years. That's just next door. Our galaxy is about 100,000 light-years across. If a civilization lives on the opposite side, their signal would take 100,000 years to reach us. And here's the subtle point people forget. Civilizations may not last that long. Human radio technology has existed for barely more than a century. The T's nothing, a flicker. If most technological societies shine for only a few thousand years before changing form or collapsing, then the odds of two overlapping in time and being close enough in space become incredibly small. It's like fireflies blinking randomly in a forest the size of a continent. Each flash is bright but brief. Unless two are nearby and blinking at the same era, they never notice each other. The speed of light doesn't just slow communication, it isolates regions of the universe from one another. Even if the galaxy is filled with intelligence, it could function as a collection of cosmic islands, each cut off by distance and time. No matter how advanced you are, you cannot step outside the geometry of space-time. And the expansion of the universe makes it even more severe. On very large scales, galaxies are receding from each other because space itself is stretching. Beyond a certain distance, galaxies move away from us faster than light, not because they are breaking the speed limit locally, but because space-time is expanding between us. Any signal sent from there today will never reach us, ever. There are parts of the universe permanently causally disconnected. So the silence may not mean emptiness, it may mean separation. Physics has constructed a cosmos where interaction is fundamentally limited. no warp drives, no instantaneous messages, just patience measured in millennia. If intelligence arises scattered across vast distances, each civilization may develop, flourish, and vanish without ever knowing the others existed. The terrifying part is that this isn't pessimism, it's geometry. The universe may be full of minds, wondering the same each trapped inside its own bubble of light speed limitations, not alone, just unreachable. We have a tendency to think of the universe as a calm backdrop, stars gently shining, planets quietly orbiting, galaxies spinning like elegant pinwheels. It looks peaceful from a distance. But that's because human lifetimes are short and our perspective is narrow. Stretch the time scale, and the universe begins to look less like a sanctuary and more like a firing range. Stars are not candles. They are nuclear furnaces balancing gravity against explosive fusion. Most of the time they behave, but sometimes they don't. When massive stars die, they don't simply fade away. They detonate. A supernova releases, in a few seconds, more energy than our sun will emit in its entire lifetime. If such an explosion occurs close enough to a living planet, it can strip away atmospheres, flood the surface with radiation, and shatter delicate biological chemistry. And that's just the familiar catastrophe. There are events called gamma-ray bursts, narrow beams of intense radiation produced when certain massive stars collapse or when neutron stars collide. They are brief, seconds, maybe minutes, but in that short time, they can outshine entire galaxies. If one of those beams sweeps across a planet within a few thousand light-years, it can destroy the ozone layer, trigger mass extinctions, and reset evolution's clock. No malice, just physics. Imagine life painstakingly evolving for billions of years. Simple cells become complex. Complex organisms develop awareness. Perhaps intelligence begins to stir. And then, from somewhere else in the galaxy, an invisible beam of high-energy radiation crosses its path. The atmosphere changes. Ecosystems collapse. The chain snaps. Evolution must begin again from simpler forms, if anything survives at all. From our perspective, that world would be silent. We wouldn't detect the civilizations that almost were. We would only see a quiet planet orbiting a quiet star, unaware that it once stood at the edge of something extraordinary. Even without exotic bursts, galaxies are dynamic places. Stars drift through spiral arms where supernova rates are higher. Orbits shift over millions of years. A planetary system that enjoys relative calm for eons may wander into a more dangerous neighborhood. On Earth, we have evidence of mass extinctions triggered by asteroid impacts, debris left over from planet formation. One well-timed collision ended the reign of the dinosaurs, not because they failed, not because they were foolish, but because gravity nudged a rock onto a particular trajectory. That's the unsettling thing about cosmic catastrophes. They are statistical. Given enough time, rare events become inevitable, and the universe has had plenty of time. So when we ask why the sky is silent, we tend to focus on intelligence, on biology, sociology, self-destruction. But perhaps the silence is older and simpler. Perhaps civilizations are repeatedly interrupted by forces entirely indifferent to them. The universe does not conspire against life. It simply operates according to its laws: fusion, gravity, radiation, orbital mechanics. These are beautiful principles, but beauty does not imply safety. The silence, then, might not be emptiness. It might be a series of erased beginnings, worlds that almost spoke, voices extinguished. Not by failure of mind, but by the ordinary, relentless violence written into the fabric of the cosmos. It's tempting to say, well, life happened here, so it must happen everywhere. That sounds reasonable, until you look carefully at how many things had to go right. Start at the beginning. Earth formed about 4.5 billion years ago. For hundreds of millions of years, it was a molten, hostile place, bombarded by asteroids, covered in volcanic oceans of lava. Then gradually, it cooled. Water condensed. The surface stabilized enough for chemistry to begin its quiet experiments. Somewhere in that messy, energetic soup, molecules learned to copy themselves. That's an astonishing step. We don't yet know exactly how it happened, but it did. Now here's the subtle part. For most of Earth's history, life remained simple. Single-celled organisms dominated for billions of years. They were successful, in a sense. Microbes are extraordinarily adaptable, but they didn't build telescopes. The jump from simple cells to complex, multicellular organisms took an immense amount of time. It required stable conditions. It required oxygen accumulating in the atmosphere. It required cells learning to cooperate instead of merely compete. That alone might be rare. Earth also benefits from a large moon. It stabilizes our planet's axial tilt, moderating climate swings over long timescales. Without that stabilization, temperature variations might be too extreme for complex ecosystems to persist. We have a magnetic field generated by a churning liquid core. That magnetic shield deflects charged particles from the sun, preventing our atmosphere from being gradually stripped away. Mars, which lacks a strong magnetic field today, shows us what that loss can look like. Then there's plate tectonics. It's easy to overlook because it moves slowly, but plate tectonics recycles carbon through the crust and atmosphere, regulating climate over millions of years. Without it, carbon dioxide might accumulate uncontrollably or vanish entirely, freezing or overheating the planet. Tectonics may depend on a delicate balance of planetary size, internal heat, and composition. Too small, and the planet cools quickly, shutting down geological activity. Too large, and conditions become extreme in other ways. And consider our star. The sun is relatively stable, not too massive, not too erratic. Some stars flare violently, bathing nearby planets in radiation. Others burn out quickly, giving life little time to evolve complexity. The sun's steady output over billions of years provided a reliable energy source, not constant in detail, but stable enough for evolution to experiment patiently. When you line all of these factors up, stable orbit, right distance from the star, magnetic field, plate tectonics, large moon, long-lived stable star, it begins to feel less like inevitability and more like a narrow corridor through possibility space. Physics allows life, yes. The laws do not forbid it. But allow does not mean common. The universe may generate countless planets with liquid water, yet only a tiny fraction may maintain the long-term stability required for complexity to arise and persist. And intelligence? That's another leap entirely. On Earth, complex animals existed for hundreds of millions of years before one lineage developed language, abstract reasoning, and technology. Evolution does not aim toward intelligence. It selects for survival in specific environments. Intelligence may be advantageous in some circumstances, but it is not guaranteed, so the silence might not be mysterious at all. It could simply reflect that the chain from chemistry to consciousness is fragile and rare, that most worlds never pass beyond microbial life, that the universe is full of biology, but nearly empty of beings who can ask questions about it. If that's true, then our existence isn't just interesting. It's improbable, and improbable things in a universe governed by vast numbers may happen, but not often enough to fill the sky with voices. There's a habit we have when thinking about the universe. We assume we arrived late. The cosmos is 13.8 billion years old. That number feels ancient beyond comprehension. So naturally, we imagine that if intelligence were possible, surely someone must have beaten us to it by millions, maybe billions, of years. We picture elder civilizations, unimaginably advanced, spreading quietly through the galaxy while we struggle with rockets and radio signals. But that assumption hides a subtle mistake. The early universe was not friendly to life. Right after the Big Bang, there were no heavy elements, no carbon, no oxygen, no iron, just hydrogen and helium. The first stars had to live and die before those heavier elements were forged in their cores and scattered into space. Planets like Earth require those elements. Chemistry requires them. Biology depends on them. So there was a delay built into the story from the beginning. The first generation of stars lived fast and died young. It took time, billions of years, for successive generations to enrich galaxies with enough heavy material to form rocky planets. Even then, early galaxies were more chaotic places. Supernova rates were higher. Radiation environments were harsher. Stability may have been rare. In other words, the clock for complex life didn't start at the Big Bang. It started much later. Now imagine plotting a timeline of the universe. For a long stretch, conditions are too primitive. Then gradually suitable planets become more common. Chemical richness increases. Stellar neighborhoods calm down. There may be a broad window, a cosmic habitable era. When the universe is finally mature enough for life to develop complexity, we might be near the beginning of that window. That's a startling possibility. Instead of being latecomers to an ancient galactic civilization, we might be among the first species to reach technological capability. The silence wouldn't mean others failed. It would mean they haven't emerged yet. Consider how long it took on Earth. About 4 billion years from the formation of the planet to the rise of a civilization capable of detecting exoplanets and contemplating cosmic expansion. That's not quick. If many Earth-like planets formed around the same time as ours, which observations suggest, then their evolutionary clocks may be ticking in rough synchrony with ours. The difference of a few million years on cosmic scales is negligible. Civilizations separated by even 10 million years might effectively overlap in the grand scheme. But if technological phases are brief, the overlap might still be rare. There's something both hopeful and terrifying in this idea. Hopeful because it means the universe isn't a graveyard. Terrifying because it places responsibility squarely on us. If intelligence is just beginning to flicker into existence across the cosmos, then what we do in the next few centuries may determine whether that flicker spreads or dies. We tend to think of ourselves as small, and physically we are. But in terms of awareness, we may represent one of the universe's earliest attempts to look back at itself. If we are early, then the silence is not an echo of extinction, it's anticipation. The future intelligence of the cosmos, the minds that will map galaxies, decode dark matter, perhaps reshape stars, may depend on whether young civilizations like ours learn to survive their adolescence. The universe may not yet be full of voices, it may be waiting for them to grow up.